and it's moving out at a certain rate, 5 meters per second. So the way you do this is first find the total flux within that loop. You have a current with z-axis, this is 20 amps. Find the total flux through the loop, and then take a derivative of the flux with respect to time and put a minus sign in front of it, and that would be the EMF showing plus and minus there. And that's really it. So the total flux, first the flux, if you have that B field from an infinite wire like that, is U0I over 2 pi, since that's Y, just Y, A of X. Now remember, it's going into the paper, so there's a minus sign there. AX comes out, if that's in standard coordinates, because X is out of the board, or out of the page. Y is going off and radially, and Z is in the vertical direction. Therefore, the B field's got a negative sense to it in terms of AX. The EMF would be the time derivative of that. I'm sorry, this isn't the voltage EMF, it's the flux that's going to cause it. So it's the integral of the B field over the area, and that will break down to this. It's really just the log 1 over Y, dy times dz times the constants. Then you get minus h. By the way, this I'm going to post on so you'll have this. So that's one of the reasons I did this. And then if this is the total flux, the voltage is minus the time rate of change of that, and that gets rid of this negative sign. So I have mu0 hi over 2 pi, 1 over y plus a minus 1 over y times dy dt. And dy dt is the velocity. Come down, it becomes this. Now there's another way to do this, but this is one of them. Once you get that, this will actually end up with a negative value because 1 over y plus a is smaller than 1 over y. So you can go ahead and get a common denominator, and if you do that, you get minus a over y times y plus a. I asked you to evaluate that at, what was it, 2 seconds? Mm-hmm. So that means if you do that, then the y value would be equal to 5 times 2 or 10 meters. And that would be the point, because it's going at 5 meters per second, and it starts at 0. All right, class? Is everybody all right with this one? If you want more explanation, I'll be happy to do it. And you end up with minus 5 times 10 to the minus 7 volts as the induced voltage. Everybody understand that? Now, the other way to do that is, if you just have, look at this, there's really, I'll draw this. I don't know if anybody, I don't recall if anybody did it this way, but the other way to do that is this. You see, you got a current here, I, and it causes a B field that's equal to mu0 I over 2 pi y in the minus AX direction. That's the B field. Well, the only portions of that actually have an induced EMF on here are going to be this and this one. So you can get the E field here and say it's just V cross B. You have V, right? Correct, class? V cross B. Therefore, you can go ahead, and if you have the E field here as V cross B, you multiply it by this dimension, L, so you get the voltage there is really V cross B. Technically, you should integrate it, but because this is going to be a constant, except it varies with time, it doesn't vary with Z, you just multiply it by the length, and this would be the EMF here, induced there. This would call it V1. This R will also have an EMF, it'll be plus or minus, and I'll call that V2, and V2 will just be equal to V cross B times L as well. Now they're actually opposed to each other. This will be less voltage and magnitude than this because this is closer. So you evaluate the B field here at 2 seconds. So if you think about it, that means this distance would be 10 meters. You find the B field at 10 meters, and you find the B field at 10 meters plus the width of that thing here. And you can do this way and it comes out the same. Did anybody do it that way? You tried it that way? Did you get it right? Or?
No.
But that's the way to do it. They are opposed, not additive. This voltage will be less than this voltage, and the voltage is in this direction. If you look at it, we've got V cross B, it means the voltage is up. Follow me? Or the E field's up. It means the voltage will be sensed minus the plus. This will be less than this. So the net value of voltage will be negative. All right, class? Let's try to put current this way. Everybody with me on that? You can do it that way too. All right, the next problem was, oh yeah, this one. I want total flux and the mutual inductance for this one. So this is like a classic problem. It's sort of a power line structure, and you got one loop, but it's not centered, it's off-centered. So here, the only thing you're going to do is find the B field from this wire in this area. And again, it's just I over, or mu zero I over 2 pi times this distance, and you can call it whatever you want. You can call it x if you want. You're going to take that B field and simply integrate it over the surface of the loop. Now you'll notice the two B fields in this area are going to be additive from the two currents. That would be the first flux. The second flux from this one is going to be into the paper. So you would integrate, basically, just the same thing, only now the range goes from 4 to 9 here. This one goes from 3 to 8. That's the difference. They're additive. The total flux, therefore, should have it down here. All right, this is V1, and the total flux is mu I over 2 pi x plus mu I over 2 pi, then it's 12 minus x, because the total separation is 12, right? So it's 12 minus x, and just dx dy, and that's really minus mu I over 2 pi, natural log of 8/3 plus log of 9/4. And there should be an h there. Should be a 5 there. That's my bad for not having it. I'll mess with that later, but there should be a 5 right here. It has to be times the height. All right, class? Does everybody understand what I'm talking about right here? Any questions at all? All right, and that will give you, this is the total flux, and then the actual induced, or I should say, the mutual inductance is flux divided by the current causing. It's the current causing the flux in the loops, the secondary loop, that you divide out. Any questions at all about this one? I gave you a problem very similar to this. I don't know if you recall it. This one, this is out of Wentworth's book. This is just the standard solid wire, has mu relative equal to 10. It's centered on the z-axis. It conducts the current with a current density. J is 4 rho amps per meter. Find the internal inductance per unit length of the wire. And I said, hint, find H and then the magnetic energy density. Then you can integrate the magnetic energy density over the interior of a meter-long section and set that equal to 1/2 Li squared. So first you have to find the H field. You find the H field by saying the integral of H dot dl is I enclosed, and therefore the H field here, the I enclosed would just be the integral of J dot ds, which is going to be rho, 4 rho times rho d phi d rho. And it goes, the integral would go from 0 to rho. Technically that rho here should have a prime on it, and d rho should have a prime too, but we're engineers, so I'm not worried about that. You end up with this being the H field, right here, 4/3 rho squared. Most people got that. And you also end up with a B field being that times mu. Then, since you have these two, well, the magnetic energy density is really 1/2 B dot H, or 1/2 mu times magnitude of H squared, and then you integrate it over the volume. The volume would have, it would be rho d phi d rho dz, and you're integrating over a length of 1 in the z direction. So you end up with this being the total magnetic energy, and that's equal to 1/2 Li squared. And therefore, to solve for L, it's simply going to be, when you take this quantity, multiply it by 2, and divide by I squared, you end up with this, and you should get this answer. And a lot of people got that right. I don't know if there was a perfect paper in here, but I know there's some very, very high scores, and I'm not sure, honestly, I'm not sure if it was a perfect one of these. But you all see what I'm talking about here? Any questions at all? The key was getting the magnetic energy density correct. After you have that, and it is a function, remember, that is a function of rho, and that's important to realize. So it wasn't a constant, it varied. And you had to make sure you had that in. All right, the fourth one was the induced EMF problem. And I think most people got this right. I don't remember what the percentage of right answers were, but a lot of people got this completely right. I was glad to see that. So for this one, I gave you a B field. This is actually a problem I gave you for homework. I just changed the B field. I think it was a sine, for the homework problem. This is a cosine. Follow me, class? So for this one, again, you're going to do the classic, and I'll draw it up here. You start by this. You're just going to have a given loop like this. And now the B field is out of the paper, correct, class? And it's coming out of the paper. And what was the B field again?
10 cosine of 120 pi t.
I'm just going to say omega is 120 pi. So omega t, go ahead.
Meters per meter squared.
You can add a coordinate system if you want. You can call that y, call this z, and come x coming out of the board. And if you do it that way, you're going to end up with the actual voltage here induced, VEMF, equal to minus d dt of the integral of b dot ds. That means VEMF here is minus d dt, double integral. The B field here is into the board, coming out of the board, so it's in the positive direction, positive AX, and that would be 10 to the minus 2. Now I'm using the milli times 10 and getting 10 to the minus 2 right here. That's the only thing I'm doing. 10 to the minus 2, and then it's going to be times cosine of omega t, and this is really going to be dy, dz in the AX direction. This has an AX sense as well, and so the dot product of the AX's is going to be 1. Not negative 1. At that point, really, I can say this is going to be equal to minus d dt of the cosine it can bring out in front, 10 to the minus 2, times cosine of omega t, right there. And then it's just times the area, whatever the area is of the given loop. And that means VEMF here is going to be, well, the derivative of a cosine is a minus omega sine of omega t. So the minuses cancel, and then I get 10 to the minus 2 times this, times a, times omega, times the sine of omega t, and that would be volts. And it's sensed positive, correct? That means if I put a resistor here, current would flow this way, correct, class? In order for a pseudo source to cause that, the pseudo source would have this polarity, and that means this is the VEMF shown there per loop. Do you all follow me on that, class? Any questions about this? And after this, it becomes a simple circuits problem, because you see there's an open circuit in the second loop on the far right. The first loop is a closed circuit. So what I can do now, I'll try to draw it right here. I can say I've got 250 ohms. This is 200. Then I have 50 here. I have an open circuit here. I put in my pseudo source this way, call this VEMF1, and I put in my pseudo source this way. They'll have the same sense to them, right? VEMF2, and VEMF1 right here is going to be equal to, really, that's going to be the B field times, in terms of magnitude, it's the B field times the area of that, A1, times omega times the sine of omega t. And the B field here is the B field in terms of the actual, sorry, no, it's the B field magnitude, not that. So I can just put that in as 10 to the minus 2. And I can put this one as 10 to the minus 2 times A2 times omega times the sine of omega t here. And if I want the voltage here, what I first get is the voltage drop here caused by VMF1, and I'll call that V50. And then I take that and I'm going to subtract this from it. So V50 would be equal to a magnitude 50 over 50 plus 200, or 250. Then it's going to be times VEMF1, and there's a minus sense to this. Matter of fact, let me get rid of that. I just call this V. There'll be a minus sense because it goes from a plus to a minus. When I start the negative terminal, this will be a voltage drop, and it will be minus VEMF2. Now, I just sketched that out because the answer's here. I don't know if I did any scratch work for this one. So, with that in mind, it really, in terms of the magnitude, is minus 10 to the minus 2 omega, and then it's A1 over 5 plus A2. A1 is really going to be the width, which is 0.5 times the height, which is 0.2, right? Or that should be 0.01, right?
Yeah, 0.1.
Oh, no, you're right, 0.1. And then this is going to be equal to 0.3 times 0.2, or 0.06, correct, class? You do that, you're going to get a value of magnitude of minus 0.302, and it's going to be times the sine. Okay. Everybody on this one? Okay. Any questions at all? Sorry, I don't have all the work shown here. But these were the last problems out of the homework I assigned. I simply changed the V field, and most, I think, every other problem was based on a homework problem I assigned. And some of these are probably on old tests too. If you look, but I can assure you that this, the way I make them up is, I go through the homeworks and I see things that are pertinent on. Any questions about this test? No? And now as far as the review goes, so it's the finals comprehensive, you did everything. I'll probably give you some equations like divergence, curl, gradient, and the like, and del squared, like in the back of the book. I'll give you those, so you'll have them available to you. I'll give you U0, I'll give you eta, I'll give you the value for eta naught at least, I'll give you epsilon naught, C, the standard constants. You work with them enough, you don't have to worry about memorizing any of that stuff. And anything else, like formulas, I'll give you the one for the characteristic, the input impedance. You know that Zn is equal to Z naught times, and it's really going to be ZL plus J Z naught tangent of beta L over Z naught plus J Z naught, plus J ZL tangent of beta L. I'll give you that one. All right, so you don't have to memorize this. I want you to go ahead and think about, bring your own Smith charts. I prefer it that way because that way you're comfortable with working with them. Make sure you bring a compass. Make sure you bring a straight edge. And by the way, when is our final?
Friday.
Next Friday?
Can we move it?
We don't have everybody here. The only way we can move that final legally is if there's unanimous consent. And we're missing how many people? 1, 2 or 3. See, I can't, I wish I could move it.
They made their choice.
They've cast their vote.
You don't understand, I can get in real trouble for this. I mean, this is not like a minor thing. If you move a final and somebody doesn't know you moved the final, and they don't show up, then I've got a lot of explaining to do. Unless further notice is given, assume the final's Friday. Is it at 8 or is it?
It's at 8.
8 o'clock Friday, yeah. 8 o'clock finals on the last day. And graduations, I don't know how many graduation ceremonies they have this time. But nobody here is graduating, but so We'll have to do it Friday at 8. I can be in my office Thursday if you have questions. If you got questions, just send it to me. It's comprehensive now. There's gonna be a transmission line problem. There's probably gonna be one or two. You know how to do impedance matching, right? All right, so stub tuning, parallel, series and shunt stub tuning. There's going to be an electrostatics problem where some charge configuration is given and you have to find the D field, E field type deal. You know that there's going to be a problem on the B field where you have to find it for a given current distribution. And some of this stuff comes together, something is added to each one of these things. You know you're going to have to find the capacitance. You know you're going to have to find the inductance. You know you're going to have to find the induced EMF in a situation with either an open or closed loop or loops or a moving bar. You know you're going to have to find for the continuity equation, say the amount of charge left, the divergence of J plus d rho dt equals 0 type of equation, and how it works. That's the diffusion equation, or well, really the continuity equation. That's part of it. There's going to be some problem on that. There may be a problem on boundary conditions. That's E tan 1 is E tan 2, it's really B normal 1 is B normal 2, H tan 1 is H tan 2, E tan 1 is E tan 2, and D normal 1 is D normal 2 unless there's charge density, right, on a surface charge density. As far as magnetic energy, that's related to inductance. So, and electrostatic energy is related to capacitance. I'm going to do something in a second, put some of this up on the board. But if you think of the major things in this course, those are the problems. And they come in large part, I go through the quizzes and homeworks and some of the class discussions too. And then I go ahead and create. I've got probably on file maybe 150, 200 problems that I've got to choose from, and I'll modify them usually somewhat. But that's the kind of thing that happens. And there's nothing here that's going to be surprising. I don't think anything on that test was surprising. I know some teachers give stuff that's really just out of left field. You have no, or right field, I should say, that you have no clue where it comes from. This stuff is pretty predictable, and I don't think there's anything on these tests that was not expected. They're not hard tests. If you want to know how many questions on, probably 6 or 7 pages. Each page has a unique theme, and this is the standard way all these things are. You're gonna, if it's inductance, you probably are gonna calculate flux or magnetic energy, and then inductance. To do that, you need to calculate the B field correctly, right? Kind of do the integral for the flux. Magnetic circuits is probably going to be on there too. The reason I say that, I haven't put this on the last test. And magnetic circuits is related to inductance. And I still have to hand your thing back to you, that homework you handed in. So those are the major things. Now, what I wanted to do now, I'm going to sketch up some stuff to show the parallels, so that maybe you can organize this in your brain a little better about how these things are all similar. Let me say one other thing too. When you're studying for a final or anything where there's a lot of concentration, you're like, it's almost like playing chess. You can't slip up at any point or you'll lose. So what I recommend people do, and this is something I've done for a long time, I don't go more than about 50, 55 minutes at a crack doing problems, and I'll take a 5-10 minute break. I first started this in college, and was based on a psychology professor that he knew that we want to know how do you study effectively. Now remember, this is not history where you just memorize, but it's analytic thought. I've mentioned this before in here, right? You do it 15 minutes, relax for a bit, get a cup of coffee or whatever, then 50 more minutes, and then take about a half an hour break, then come back and do the same thing again. It's worked for many people besides myself, but if you don't take that break, what happens is you get fatigued and you'll start daydreaming and losing concentration, everything like that, and then you can't retain stuff. I don't know if anybody else has tried this, but that's the legitimate truth. And they'll tell you this because that kind of concentration that you need to do these problems and study, a lot of it means you need to be, I guess, as refreshed as possible. You can't do that on low sleep. You can't do it with a cajillion tons of caffeine in you. You won't remember anything. And you can't do it with a lot of distraction. So I always tell people, as best you can, get isolated. You can work in a group, but make sure the whole group's working on the same thing. Now, before I start, do you have any questions at all? Any problems you want me to do? Any concepts you want me to talk? Here, it's one of these odd things. Some classes have got a list they want me to go through, and I don't have enough time. Some classes are like this class where you've got nothing for me because you were just waiting for your test. Here's what I'm going to start with. For Smith charts, really, this is going to be for chapter 2. Right? In chapter 2, we're talking about transmission lines. Remember, I give you Zn is Z naught times ZL plus J Z naught, tangent of beta L over Z naught plus J ZL, or Z naught, ZL, pardon, tangent of beta L. That's the input impedance for a lossless line. I'm not going to give you a lossy line, I'll tell you that. So if we have a transmission line and there's a load here, and that's characteristic impedance of Z naught, then that's the input impedance, Zn. Make sure you understand that. I'll give you this, right? This is how it applies. That's the input impedance of a transmission line. Now, at that point here, the next thing you think about is, well, what's this used for? It's used to solve a complete circuits problem. So if I have something where I have a voltage source, plus to minus Vs here, and it has a source resistance or impedance, and now I have a transmission line of a given length L, and I have a load here with ZL, and I want to know this voltage right here, based on this voltage, and this voltage will be given as either a sine, cosine, or just magnitude at angle. Let's say it's going to be V naught at an angle theta source. Now this is classic, the way you do this problem, and I'm going to add a few more equations. We haven't done this in a while, that's the reason I started. The first thing I have to do is get the equivalent circuit to this that I can work with. So I need first Zn, that's the first thing I get. And I get it using this equation right here. I have the length, and remember this is at 0. The way we do it, the load's at 0, that's Z, and this dimension is L, that's the length here. Now, the equivalent circuit would be one where I have plus to minus the source at the angle of the source here, source resistance, and then I have the equivalent Zn here. And I'm after this voltage, and that is my V prime. That's the voltage just on the inside of the transmission line. And what is V prime based on this circuit? That's Zn, by the way. Just tell me.
It's going to be Vs times
Vs at an angle theta S times, go ahead.
times VL over VL plus
Zn.
Sorry, I don't know.
Zn over Zn plus Rs. So now we have that, right? That's the voltage just on the inside of this transmission line right here. Once we have V prime, we also know that V prime is equal to V naught plus times E to the minus J beta Z plus the reflection coefficient times E to the J plus beta Z at any point, right? That's, I should say, that's V at any point on the line. When you're at Z equals minus L, this becomes plus, and this becomes L, and this becomes minus, and this becomes L. Correct, class? Everybody with me on this? Now you remember this, but just make sure you know how to use this. Because I could give you information where I say, this is what V prime is right here. Follow me? I don't have to start right there. Or I could say, this is the load voltage, what source voltage created that voltage. Follow me? So there's a lot of different ways this problem goes. You just have to understand all aspects of it. Now that means, since I have V prime, I need V naught plus, and that's going to be my V prime, which is down here, divided by E to the J beta L plus reflection coefficient times e to the minus j beta L. And the reflection coefficient, I'll get out of your way in a second. What is the reflection coefficient? It's at the load, correct? And what is it? It's always the impedance you're looking into, right? Minus the impedance you came from over ZL plus Z naught. So that's how I get that gamma L, correct, class? Now I have that. That's V0 plus, and I'm looking for the voltage at the load. What would the voltage at the load be? Well, this is the general equation of these were Z's, right? What is Z at the load? 0, and that means it's just V0 plus, right? Times e to the 0, and I'll just put it in. It's going to be 1, simply 1 plus the reflection coefficient at the load, right? And that's, in a nutshell, how you do this problem. Now that's the voltage. What's the power at the load? The power being dissipated at the load.
Half the real part of
Well, really, power is what? It's going to be 1/2 times the real part of V times I conjugate. We know this is going to be 1/2 the real part of V, right? Well, we got the voltage at the load, right? And it's times I conjugate. That's the voltage at the load right there. And that has a magnitude and an angle. Well, I is what? It's V divided by Z, right? And if we conjugate that, we can just take VL divided by Z and conjugate it. Now, the only thing that does is take the angle, and it's a combined angle, because Z could have an angle too, right? And if it's whatever that angle is, it makes it negative, that angle. That's all it is. And you just multiply those and take the real part. Now, the thing is right here when you do this, all right, there may be an angle left. All right, there may not. You don't know that until you do it. But he has more information about this in his book. You can see stuff, but this is the way you do it. Now you have the power of the load. And the real part is just going to be, if you have like V naught e to the j 30 degrees, say there's some value, k e to the j 30 degrees, the real part is that's going to be the k times cosine of 30 degrees. Do you follow me on that? It's always going to be the cosine of that angle. With me? Okay. That's that. If I asked you for the standing wave, voltage standing wave ratio, this is the one people mess up all the time. Do you remember what it is?
1 plus the reflection coefficient.
1 plus the magnitude. Don't forget the magnitude. People do that and they get wrong answers because that reflection coefficient in general is complex. 1 plus the magnitude of the reflection coefficient at the load over 1 minus the magnitude of the reflection coefficient at load. Now, if the reflection coefficient is 0, in other words, if it's perfectly matched, the standing wave ratio is 1. The ratio of the maximum to the minimum voltage is 1 because all waves are propagating this way, and the min and max will have the same value. Otherwise, it's going to be greater than 1. It's never less than 1, okay? And if I give you this reflection coefficient, then you can, by the same, if I give you the reflection coefficient right here, or the voltage standing wave ratio, you can calculate the reflection coefficient. Got me on this? So you have to know the interplay between all these things in order to do these problems. That's a standard complete circuit problem. I want to make sure you know how to do. We haven't done it in a while, so I put it up. The next one is impedance matching. And remember, when you do impedance matching, things can be put in parallel or things can be put in series. And this is important. So, we have this for impedance matching. We'll do one where we put it in parallel first. So I've got a system like this, and this is Z naught, and I'm going to say there's an impedance mismatch. ZL is not equal to Z naught, so I want to put a stub in shunt here, right? The way I do that, I know it's going to be at a distance here, and this is, in Wentworth's book, this is called, I think, D through. I'll just call them. And then I attach a stub, like so, and the stub length is D stub, right here. And I'm gonna make it short circuit, but it could be open circuit, right? So the way you do this problem, first thing, you need a Smith chart, and there's the one circle. The first thing you do is find the normalized ZL, and that's ZL divided by Z naught, and you plot it. And I'm gonna just pick a point. I'm gonna pick it right here. So that's my ZL. Now, because we're adding in parallel, I know if we're gonna add anything in parallel, we go to the admittance domain. If we're adding in series, like if this stub was in series, then we'd work in the impedance domain. Does everybody understand that? But we're in the admittance domain. So the next thing I do is get YL is 1 over ZL. That means to get YL, you draw a straight line through here, and you're really going at the conjugate point. This is point 1. Label your points when you do these two, by the way. And that's YL, right? Now, at that point, everybody with me on this? I mark the out part of the circle right here, and I'll call point A, and that's wavelengths towards generator. Because we're moving away from the load, we're going to be moving towards the generator. Okay? Right here, that A signifies the distance. They call it a mile marker. It's the outer edge, correct, class? Remember, wavelengths towards generator. Now, I'm going to move on a circle that has this radius. Well, these things should go through each other. However, it's not a very good circle, but you get the idea. I move along this circle until I hit this point, because that's the 1 plus J something. So when I hit this point, that's point 3, and now I know I have a point 1 plus JX. I know that for a fact, correct, class? And the X just represents whatever the value is of the the imaginary part. Now I take my rule and put a straight line through here, and I look on the outer edge, and I get point B, and that's wavelengths towards generator. That'll be a number. And those are always fractions of a wavelength. Then I find the distance, D, or I should say D through, and that's equal to this value, B, always the point you landed at, minus this value, A. Now, that's going to be negative, I think. And if it is negative, then you add 0.5. You can always add 0.5, always. The thing is, sometimes you get one that's longer than half a wavelength, which is kind of stupid because you're wasting transmission line if you think about it. You want the shortest possible stub, you don't want the longest. With me on this, class? If it's negative, you add 0.5. Now, we deal with the stub, the actual shunt stub. So I know when I have a shunt stub, this is the stub. For a shunt stub here, what is ZL? 0. Make sure you get this part, right? That means when I normalize it, ZL normalized is still 0, correct? Now I get YL. YL is 1 over ZL, and that is infinity, right? So when we're right here, the impedance of this is infinite. And we come in right here. This is the infinity point. This is the 0 point, right? On a Smith chart. Now, how far do we move? Well, this is JX, right? I left it positive. It could be negative, right? There could be a minus JX. But now, I'm going to move until I hit the point here, minus J or X right there. With me? And those are the lines that are perpendicularly intersect there. Right at that perpendicular intersection, you'll read these values that you're going to use. With me, everybody, class? All right. And then I go from here, and this is 0.25 wavelengths towards generator, that's that point. And I subtract off, then I have to take a line, make sure you do this right too. You gotta take a line right through there and you have to read that point, and that's part C and its wavelengths towards generator. And I find this stub length, therefore, the stub is going to be equal to C minus 0.25. Everybody with me on that? And that's
So the 0 and infinity you put up is admittance, right?
same for impedance. Right? If we're in the impedance domain, that'd still be infinite, that'd still be 0, but we're working in the admittance domain. The Smith chart works for you. I mean,
I thought,
I think I know where you're getting confused. You're saying, well, wouldn't this be a 0 impedance, right?
yeah,
Yeah, it is, but when you're working in the admittance domain, the entire Smith chart then is going to be, all these values are going to be admittance values. All right? You're only in the admittance domain. You're not in the impedance domain. I do know how you can get confused on that. With me on this, class? All right, and that's how you get the distances here. Now, if this was open stuff, right? If this was an open, how would it change? Let's just make it open. What changes fundamentally? Does the point right here change? No. Not at all, right? What changes?
The D stub.
The stub. If this is an open, right? Then ZL is YL. This might answer your question better. I mean, ZL normally would still be infinite, right? And what is YL? 0. So now where do we start?
0.
Right? We'd start here, correct, class? And we go how far? This one's going to be a long one. If that's a plus j, x, right? We still need to get the minus j. So we go a full quarter wavelength and then back to here, exactly, right? So really that length will be a quarter wavelength longer than a short circuit stub. And that's nice to remember. Okay, every quarter wavelength, whatever impedance you had becomes your admittance. You go exactly that far. Okay? By the way, one other thing, looking at this Smith chart, we can use the actual, your Smith chart, make sure you have this, you can use the simple measurement of this circle from here to here to get the reflection coefficient, right? And we can get the angle too by looking at the, if you just shoot a line right there from where you came in at, right here, you can get the angle of the actual reflection coefficient, right? So you can get that, and you can also get the standing wave ratio. On most Smith charts, they have a standing wave ratio. Really a legend that allows you to do that. And we could do series too. Do you want to do a series stuff? It's been a while, that's the reason I'm spending more time on this. I mean, does everybody know how to do a series stuff? All right, let's do one. Let me erase this and do a series.
so for the open, your C wouldn't have a 0.25 in it because you started from 0, right?
Well, the length of the stub is always positive, right?
Yeah.
Either I start from here, this is going to be greater than this, right?
Yeah.
So it's always positive. From here, this point's always greater than that, but you never have to worry about moving from this to this where you can get a negative number. Okay?
Okay, the answer to your question is yes.
Okay.
How many have finals in another class besides this one? What day are they?
Wednesday, Thursday.
Wednesday.
Okay. Well, you got time to study it. All right, next, we're going to do series. So we'll start by saying this is what it looks like. I have a ZL here, and I want to put a series stub. Series means like this. I can be a short circuit series. So this is going to be my D through right here, and this is going to be D stub. Now it doesn't matter if it's open or short. in reality, almost all the time, I believe they use short circuit stubs, because an open circuit stub means you're gonna have a potential, a positive to minus potential at the end of that thing that can cause stray the electric field can actually penetrate or map into other components. And that's the reason, as far as I'm concerned, just about, I can't think of a good reason not to, they use short circuits. Somebody can probably find an example of an open, but I don't know of anybody that designs things with open circuit stubs. All right, so this has a characteristic impedance Z0. Now, for this one, put a Smith chart up. We try to. Get the one circle here. And now, first come in and you get Z normalized. Load is ZL over Z0, so that's 0.1. We can kind of do it the same. There's 0.1 here, and this is normalized ZL. Then go ahead and draw a circle around here, right? Then you have to take a straight line and move it out here, and that's point A, and that's wavelengths towards generator. Now you're going to move in the impedance domain until I hit here, correct, class? And now I move this far from here to here. And that's going to be B wavelengths towards generator. So I can see that my B through is going to be equal to B minus A. And, you know, if we were down here and had to do this and it was negative, we'd add half a wavelength to that if it's negative. Okay? Make sure you get the point you landed minus the point you came from, and wavelengths towards generator. Once you have that, now this point, that's 0.1, this is 0.2, and this has a value of 1 plus JX. So if we're adding impedance in series, I need to add a minus JX, right? Now follow me on this one. I use the short circuit stub. And we want to get this distance. So the stub has an impedance of 0, right? The normalized impedance is 0. It's got a characteristic impedance of Z0. By the way, if it didn't have a characteristic impedance of Z0, the normalized still is going to be 0, correct? Sometimes some professors, they'll do this, they do this, I don't like it. What they'll do is put a different characteristic impedance, which means now you can't work in the normalized domain. You have to work in the actual impedance domain because the characteristic impedances are different. I'm not going to do that to you, I'm going to tell you that, but you'll get that in microwave if you take it with Dr. Wentler or whoever teaches it. Anyway, I want to figure out how long this is. Well, I have to have an input impedance here of minus JX normalized, correct? Right? All right, well, how far do I have to go? First, for this one, ZL is 0, right? We're working in the impedance domain. Where's 0? This is infinite, right? This is 0, so I start here, don't I, class? And how far do I go? I have to go a full quarter wavelength, right? And then some. So now I've got to move from here, right, all the way to the point here where, on the circle where I hit minus JX. Wherever that point is, I come out here, and then I look at C, and this is wavelengths towards generator, and I can say that D stub is equal to just C, because this is, if it's 0, I don't have to subtract anything. Agree, class? So that's series, a series stub. Most of the stuff that I know of, and I'm not an expert on this, is shunt. That's the way it's usually done. But series can do too. I only think that it's usually shunt for one reason. It's done on copper-clad boards usually, and that means it's real easy to make them in parallel because you're going to just etch out copper on one side and then put a shorting bar at the end of that. It's easier to do. Series is a little tougher to do on this. Okay. All right. So that's something to review. The chapter we haven't been at the longest. Then the one after that is electrostatics, but that's related to capacitance too. For electrostatics, I'll put some I'm gonna do this in a way where I show the similarities between electrostatics and magnetostatics. So, first, if we deal with electrostatics, we know that the actual force is equal to QE. That's the force. Next, we know the E field in general from a single charge is equal to Q over 4 pi epsilon naught R squared, right? AR. And AR is a unit vector in the direction emanating from the charge source to the point of observation. That's for a single charge. You can say that the differential E field from a volume of charge is just equal to dq over 4 pi epsilon naught R squared AR. And therefore the E field from a bunch of charge is really equal to dq, whatever that may be, over 4 pi epsilon naught R squared AR, right here, integrated. Now dq can be given as either rho L dl, right? That's if it's a line charge. It can be given as rho S ds if it's a surface charge, or it can be given as rho V dv if it's a volume charge. So it depends what you're dealing with, volumetric, surface, or line. And then, I mean, the evaluation of this is something that it really has to do with the coordinate system you're in, but it's usually straightforward. By the way, this is can be complicated. In general, it can get very complicated. And that's why we go from there. Well, let me say this. From there, then we use what law to simplify? Gauss's law, right? We say Gauss's law says that the integral of d dot ds over a closed surface is equal to the integral of rho v dv over the charge within the surface, contained within it. Something else I didn't put up, but you have to know the coupling effect. D is equal to epsilon E, you have to know that, right? And you have to know B is equal to mu H, these are similarities, right? Then you have to also know that J, right, is equal to sigma E here, right? And if you have that, there's one other thing, divergence of D is rho V, or the divergence of E is rho V over epsilon, right? And this is Gauss's law and makes life easy. And a lot of times for highly symmetric problems, we know really it's the D field is going to be 1 over the surface area, right, times the integral of rho v dv. And the surface area for a sphere is 4 pi r squared, because you're going to be at a constant distance. It has to be a highly symmetric case in order to do this. Or if it's cylindrical, the surface area is just 2 pi rho times the height, right? But it's always the surface area of the symmetric surface you're talking about, correct, class? And really it's used for cylindrical or spherical primarily. There are some planar ones, but not often used for. So that's the D field. And because of the relationship, if you have D, you have E. Just divide by epsilon, right? All right, now, one other thing with the electric field, and that is that if we say that the E field is equal to, and this is only for electrostatics, so statics means nothing varies with time. Electrostatics, nothing electrically is time varying. You can't have a time varying charge and do what I'm about to do. For electrostatics, E is minus the gradient of V, correct, class? Right? Now, with that in mind, I can go ahead and say, well, the divergence of E equal to rho V over epsilon means the divergence of minus the gradient of V, because E is that, is equal to rho V over epsilon, or we get del square of V is equal to minus rho V over epsilon. And that is Poisson's equation. That's in the differential form, right? And you have to be able to handle that and know how to use it. And then you can also say that the volumetric form for V would be given as the integral of rho s over, or really rho, over 4 pi epsilon naught. Let me just do it this way, I'll put it as dq. Epsilon naught divided by r, and there is no vector sense. And dq again would be either rho l d rho, or rho s ds, or rho v dv. And that's the voltage assuming v at infinity. V as r goes to infinity is equal to 0. And that's something you have to understand, how to get the voltage difference between points. And remember also that the voltage is equal to minus the integral of E dot dl. And this is, I gotta put some systems down here, so that's from V A to B here. And that would be minus that, the integral from A to B. Or actually, I'm sorry, from, this is gonna be A here, and this is B. And that's the voltage in an integral form based on the E field, using the E field. Right? Now the similarity with this, a lot of this in the B field, right here, you know that the value of B, or really H, let me do H, H here is equal to I, the differential H field, when we talk about the differential H field, we say that's equal to I dl crossed into AR over 4 pi r squared. It's similar to the E field, differential E field, except there's a crossing, there's a cross product. And the dl has to do with the direction of the current element that's causing that. The total H field, of course, is simply the integral of dH over the actual, over the total current that's causing the H field. This is very similar to this right here. This is what? That's the, that's really Coulomb's law right here, isn't it? And this is the Biot-Savart law, right here. I don't care that you don't have to know the names, just have to know the mathematics of this. All right, well, you can see that there's also something that comes next that has to do with highly symmetric cases. And then you can use something, this is Ampere's law, right? And Ampere's law says the integral of B dot ds is equal to really the I enclosed, or it's the integral of J dot ds. Let me do it this way, pardon me. Let me write it this way. The integral of H dot dl is equal to the integral of J dot ds is equal to I enclosed. We'll do it. What I said before wasn't right. Okay? And usually for this, you're talking about cylindrical systems, almost always. And that means really H times 2 pi rho, which would be the circumference when you're at a distance rho. H is given as 1 over 2 pi rho times the integral of J dot ds over the surface. That's usually the way you're going to see the application of this law. We have that, okay, that's the contrasting. By the way, what is divergence of B, by the way, class? It's 0. Here, divergence of D is charge density, right? There's an electric charge density somewhere. Yeah, that's the electric, that's real charge, coulombs per meter cubed. But there's no such thing as magnetic charge, except at 10 to the minus 15 seconds after one of those CERN reactor collisions, there's the existence of magnetic charge for an instant. But for all intents and purposes, it doesn't exist for our applications. That's the similarities. The next thing we talk about is the relationship of capacitance and inductance. And so for over here, for capacitance, we know C is equal to Q over V, right, in general. And the way you get this is usually you assume either Q or V, but assume Q. After you do that, you get D. After you do that, then you get E. After you do that, you get V, and then you get C is equal to Q over V. That's the usual way of going about it with a problem that I ask for capacitance. If I ask for resistance, I know R is equal to V over I. And usually, not always, but you can assume I. Then after that, you get J. After you get J, then you get E is equal to really J divided by sigma, correct? And then you get V, right? V is equal to the integral of V dot dl, with a minus sign. And then you go ahead and you get R is equal to V over I. That's a standard way of doing business. For inductance, the normal thing you do is going to be, for an inductance problem, you either assume I, or it's given, or J is given explicitly. It's one of those two. So from I, H, from H, B, and then you have a choice. You can go one route where the next thing you do is get the magnetic flux as the integral of B dot ds, and the actual inductance is equal to the flux divided by the current causing it. Now there's one caveat here. There's also a factor of n if there's turns involved, and that's something you have to be aware of. And this is the way to get inductance on a flux basis, where it's like the solenoid, the toroid, things like that. The next way is you start with I, then you get H, then you get B, then you get the magnetic energy density, which is 1/2 H dot B, or 1/2 mu H squared, and then you get the total magnetic energy as the integral of Wm over the volume, and then you set 1/2 Li squared equal to really the magnetic energy right here. And you can therefore find L by saying it's 2 times the magnetic energy over the I squared that caused it, right? That's the magnetic energy density. I didn't say this with capacitance, but you can also do that for capacitance. You can start the problem this way, but at this point, instead of just getting V, you can get the electrostatic energy density, and that's 1/2 times D dot E. That's called the electrostatic energy density, or 1/2 times epsilon E squared. And then you can go ahead and integrate the electrostatic energy density over the volume and put that equal to 1/2 CV squared. We can do that and solve for C. With me, class? So I'm trying to contrast the similarities in these things. There's a huge amount of similarity in the way the equations are structured and the applications. Gauss's law for getting D field in one region, DE, and if it's electrostatic. We use Ampere's law to get the H field, highly similar cases, if we're talking about magnetics, right? And the magnetic circuit, well, I think you're okay with that one. Everybody scored very high on that, so I'll put those outside my office, all right? And you can come by, pick them up later. I don't think I need to go over that one. We just went over chapter 5 material, induced EMF, and time varying electric fields. The one equation we weren't really tested on was this one, and that is the continuity equation where divergence of J plus the partial of B with respect to T equals 0, right? Do it this way. That's rho V. It's divergence of J plus d rho V dt equals 0, right? Or you could actually say that if J was equal to sigma E, then you can get this as sigma over epsilon rho V, because divergence of E is rho V over epsilon, plus the rho V dt equals 0, and rho V is equal to rho V 0 e to the minus t over tau, if if there are no other forced charge sources, but I'll just leave it as that. We've done problems like that, Ron. And that's sort of I didn't get to chapter 5, but we've just done chapter 5 material on the last step. But that's sort of a review of everything you should be aware of for the test. And again, most of these things, you'll see the similarities. Right? I'll give you, the curl, gradient, Laplacian, and divergent, and all the coordinate systems. And that Zn formula, I might give you a few others, I'm really not sure, but that's it. Now, it seems like a lot, but think about it. If you've been doing your work, then a lot of this stuff you probably got down. You just need to brush up on a few of the finer points. Any other questions before we break up? If possible, I would love to change the final. And who's missing? Andrew and is anybody else missing? We got 2, 4, 6, 8, 10. Who? We got 2 gone. Yeah, we're missing 2. Yeah, we're missing 2 of them. And that means you're going to be unable to move that far. But how I would love to.
Can you email them?
Yeah, where's the face?
He ain't like
I'm curious. All right, let me ask you this. What does Tuesday look like for you? Bad or good? Bad. All right. Tuesday's bad.
Fun on Wednesday.
All right. What does Monday look like for you? Good or bad? Bad? What looks good? Let me try that approach.
I'll just like it later in the day.
No, I'm fine with moving it, but time-wise, but for me to move it, I gotta make sure everybody moves it. What day you wanna move it?
Friday's probably the best day.
Just like later in the day.
Yeah.
There's 2 things I have to do if we move a final. First, I gotta make sure it's unanimous consent and everybody can be there. Second, I have to find a room that's open. Usually you can find a room in the summer, usually. The problem is unanimous consent. So what time?
Is like noon, okay?
You're like 1.
On what day?
Friday.
I think everybody wants it earlier.
They want it earlier.
Except you.
No, I want it early.
When do you want it?
Oh, go ahead.
I'd want a Wednesday or Thursday.
Well, see, other people have finals Wednesday.
So do I.
You want to take 2 finals?
Yeah.
Sunday?
It means I don't have to be here on Friday.
You're sick.
What time is yours on Thursday? Would you move it Thursday or no?
No.
All right, here's what I'm gonna do. How about I point Jared as somebody that gets the unanimous consent and a time for me? That way, I can't get in too much trouble. Will you agree to that? See,
Find a time.
first see if there's any time besides Friday at 8, where everybody would agree to it. Then after that, make sure that you give me proof that everybody has agreed to it by an email. And then I'll see through Dr. Nelms if I can find a room that's available. Those are things we need to do. I'll put it in your hands, because here's what happens with me. Thursday night.
Yeah.
No, actually, because we have a test that morning, then we have the whole day study.
Hey, I'm cool with that too. But the only thing you gotta do is this, make sure you can get into the building.
That'd be the only thing I would.
There's a door in the back, you just have to input the code or whatever you want.
All right, but we need, again,
Yeah, unless you want.
unanimous email verification that everybody's okay with it, not some kind of fake email. And then the second thing is I gotta find a room. But why don't you just talk about it yourselves? I'm cool with anything. I prefer doing it earlier, not Friday. But by the same token, I'm not the guy that makes these choices. That was given to me. I don't schedule the final, somebody else does. All right, that's sort of it. You know what's coming, about 6, 7 pages. Bring your own Smith charts. I'll bring some in case you forget, but I prefer you bring your own because you're more familiar with it. And that's it.